In this video, we are going to look at how we can implement class for stacks in C++. And to be able to do that, what I need is an underlying data structure, because remember, stack itself is just the description of the operations and how they behave. So what I need is an underlying data structure to implement this idea. So underlying data structure. And in this video, I'm going to show you two possibilities for that. Namely, I can use an array as the underlying data structure, or a linked list. And I'm going to use the simplest kind of linked list, which is a single linked list without a tail pointer. Okay, and on top of these, whichever I choose, I will build the operations that I need, which are push, pop, top, and empty. And I will also talk about the time complexity of each one of these operations for each option for the underlying data structure. So let's start with arrays, and let's see how we can implement a stack using them. So implementing a stack using an array as the underlying data structure. Okay, so you will define a class called a stack, right? Obviously, and then the member functions are going to be push, pop, and so on. We will explain how each one of them work. But in terms of the member variables, what you need is an array and also an integer that I'm going to call size. Okay, and then when you create an object of this class called the stack, the constructor, which is the create operation, creates an array of some fixed capacity. Okay, let's say the starting capacity is 8. So your constructor creates an array of size 8. So 0, 1, 2, 3, 4, 5, 6, and 7. So that's one member variable. You have A, which is the name of the array, or you can think of that as the pointer. You can call this whatever you want. And that's one of the member variables. And as I said, the other member variable is something called size, which represents the number of elements that are currently in the pushed into the stack, which is at the beginning 0. So that's what your constructor should do. It should use the new operator to dynamically allocate memory to an array. And you can use templates, for example, if you don't want to fix the type, and so on. And also it initializes the other member variable size to 0. And basically that's all there is to it, these two member variables. Okay, and now we can talk, and obviously I'm using 8 here so that we can visually show you, but 8 is too small, so maybe you start with like 500 or something, depending on your application. And then we have to talk about each one of these operations, right? So let's start with push. Okay, let's see what should happen if I say push 5. So I created this stack called S1 or something, and then I say S1.push. So I call this member function called push. Now what should happen? What should happen is the following. It's very simple. So first of all, you write 5 in the first position in the array. Okay. And since now we have one element in the array, our stack is not empty, the size of the stack is now 1. So we update the size by 1. So in terms of the code, you say A at index 0 equals 5, and then you say size plus plus. Okay? And then if I push another element, let's say push 14, for example, 14 will be written next to 5. So 5 and then 14. So 0, 1, 2, and so on. And then you update size to 2. So very simple, right? Now, in general, when you push a new element, what you need to do is you need to look at the size, and that number tells you which index you should write this new key at, right? So when the size is 1 and you push a new element like 14, then 14 should be written at index 1, right? When the size is 2 right at the moment, you already have 2 elements. If I push again, this element should be written at index 2. So whatever size is, that's the index that you write the new element at. And of course, you update the size by saying size plus plus. Okay? Now, one special case that I will talk about later is that if the array is already full, then you have to do something different, right? And that's when size is equal to the capacity. Like you create an array of size 1,000, then when the size is 1,000, it means that you already have 1,000 values in your array, which means that if you push a new element, 1,001, then you have to do something about it because there is no room. And what we do, we have two different options. I will talk about that in a few minutes. Okay, so that's push. And as you will see, what we do when we perform one push is we look at the size, go to that index, whatever size says, index 1, index 10, and so on. And then you write that new value there, and then you update the size by saying size plus plus. And none of these, the time that they take depends on the size of the array, on the capacity of the array, I should say. It doesn't matter if the capacity of the array is 10,000, 15,000, or 15, it takes the same amount of time. So we can say that push is a constant time. Okay, I still need to talk about the special case when the array is full, but I'll do that at the end. Okay, so that's push. If I want to do one more push, okay, so I push 4 this time. So what I do is I look at size. I already have 5 written here and 14 written here. I look at size. Size is 2, so I go to index 2 and write 4 there. And then I say size plus plus, so size becomes 3, right? So very simple and constant time, very important. So push in this implementation is constant time. Now, what about the other operations? What about pop? So if this is the current state of my stack, and then I call the pop, like the name of the stack is S1, and then I say S1.pop. Now, pop is supposed to remove the most recently added element from the stack. Now, in this case, the most recently element added is this 4 here. So I need to remove 4. But remove in quotation, because what I need to do here is I just decrease the size by 1. So if I change the size to 2, it means that there are only 2 values in the stack, which means we are only looking at 5 and 14 as the actual data stored in the stack. And even though 4 is there, since the size is changed to 2 now, that 4 will not be treated as actual data. So 4 will be treated as garbage, which means that if next time you want to push something, we overwrite 4 with that new key that is being pushed into the array. So pop is simply size minus minus. You decrease the value of size by 1. You don't write anything in the array. And obviously, that's also constant time. So far, everything is good. Push is constant, pop is constant in terms of time. How about top? Okay, so after doing this pop thing, my current state is the following. I have this array of capacity 8. I have 5 written here and 14 written here and 4 written here, but the size is 2, right? Because I decrement the size. So size is 2. Now top is supposed to return the most recently added element. And since 4 is removed because of this pop, the most recently added element is 14. And size tells me that, because when size is 2, it means that there are only 2 values in the array. So the second value is the most recently added one. So what I need to do is I need to return whatever the name of the array is, A. I need to return A at index 1. Now, where does that 1 come from? It's 2 minus 1, or size minus 1 in general, right? A at size minus 1 is what we return. Because, again, one more time, size tells you how many elements you have in the array at the moment. And then the last one is the most recently one, which is the element at index size minus 1. And that's what top returns. And obviously, this is also constant. Okay? And empty, if you think about it, if you want to check whether or not a stack that is implemented this way using an array is empty or not, is checking the size. You don't need to look into the array at all. You look at the size. If size is 0, then the stack is empty. And if it's not, the stack is not empty. So you just return size equals 0. So if size is the same as 0, then you return true, otherwise false, right? And this is also order 1 time constant. So all these operations are constant time, right? Push is constant time, pop is constant time, top and empty are also constant time. The only thing left is this special case for push that I mentioned briefly, which was, what if, let's say the capacity of the array is 8, and we already have 8 elements in the array, right? Size is equal to the capacity. Then what? Then how do we push a new element? Okay, so the last question for this implementation is, what if the array is full and we want to push a new key into the stack? Okay, so what should we do then? And the answer is, you have 2 options, and each one has its own benefits. So option 1 is sending an error message. Okay, throw an exception, for example. You say the stack is empty, the stack is full. Sorry, we cannot push any new elements into the stack. That's one option. It's a valid option as well. It's not ideal, but you can start with a large enough size stack that you're sure that this doesn't happen very often. And then if it happens, you send an error to say, sorry, we cannot push this new element because the stack is already full, right? That's one option. Option 2, if you don't like this option 2 is what's called the doubling the array. So double the size. Now in C++, this takes a little bit of effort, right? So let's say, for simplicity, let's say the capacity was 4. So instead of 8, I'm going to start with 4. So I created this stack by allocating memory to an array of size 4, or I should say capacity 4. And at the beginning, the size is 0, obviously, right? And then I had 4 pushes. So I pushed say 10. So now the size is 1. Then I push 4. Now the size becomes 2. Then I push, say 7. The size is 3 now. And then I push 8. And now the size is 4. And the capacity is also 4, right? Remember, capacity is another variable that we have. So we have the array, the size of the array, which is the number of elements, and then the capacity as a separate variable. And the capacity is also 4. So now size is equal to the capacity. So if I want to push again, say 11, I look at the size, compare it with the capacity, they're equal, which means that I don't have room for a new element. Okay, now instead of sending an error, what I can do in this case is I can create a new array. So the push has this code in it, right? So the push says if size is equal to capacity, then don't insert anything yet. And what you do is you look at the capacity, which is 4. You allocate memory to an array of double the size, in this case 8. Then you copy everything from the old array into the new array. So copy 10, copy 4, copy 7, and copy 8. Deallocate the memory allocated to the old array. And then perform the push, which means size is still 4. Right? We didn't change the size yet. So go to index 4 and write 11 there, and then update the size. So now size is 5. Okay. But now capacity is not 4 anymore, capacity is 8, which means that I still have room for 3 more pushes. And then if I do 3 more pushes and without any popping, and then do another push, then I have to double the size again and go with an array of size 16, copy everything, and so on and so on. So this is called, doubling the array. And that's also a very, common solution to this problem. Okay. Now, the disadvantage of sending this error is the inconvenience, right? In some cases you have to say, I can't do what the user is asking me to do. And it seems like this is a good solution, but it comes at a cost. The cost is when you do this doubling, the process of doubling the array is not constant time anymore, because you have to read these values from the old array and then write them into the new array, and you have n elements here. That takes order n time. So doubling is time consuming, right? If you have n values in the array already, then doubling the array takes order n time, not because creating the array is time consuming, but because you need to copy the data one at a time, right? Copy the keys one at a time. But it's not as bad, and order n seems very slow, but in this case it's not as bad because this process of doubling the array doesn't happen frequently. It happens occasionally if we reach the maximum size, right? So since it doesn't happen very often, but does not happen often, and I don't want to get into this because it's beyond the level of this series, but in an algorithms course, there is a way of analyzing this called amortized analysis. And we consider how often this happens, and then we take the average. But the overall result is that still on average, the running time of push will be constant. Okay? So using amortized analysis, still we get constant time for push on average. So once in a while, average push is going to be slow because you need to double the size of the array and copy and all of that. But on average, still it runs in constant. Okay, so that's it. That's how we implement a stack using an array. Now, to review one more time, the idea is that you have a class called stack, and what it does is that when you create a new stack object, it allocates memory to an array of a given capacity. You fix that number to something, and then you have a variable called capacity. So in this case, capacity is 8. You create an array of capacity 8 and set another member variable called size to 0 because there is no element in it. If you want to push something, you look at the size, and that tells you which index you need to write this new key at, and then the next one, and the next one, and the next one will be written in the next index. Every time you need to push, you increment the size by 1, and that is constant time. Occasionally, you reach to a situation where the array is completely full, which means the size is equal to the capacity. In that case, you need to double the array, copy everything from the old array into the new array, and then push the new element and increment the size. So that takes order n time, but since it happens rarely, still on average, you get constant time for push. Okay, and the time complexity of different operations. So push is, in the worst case, order n, but on average, constant time. Pop is constant time. Top is constant time, and empty is also constant time. Okay. In the next video, we are going to look at how we can implement a stack using singleton.